All right, let's talk about the binary index tree. So let's assume we are given an original array, right? And let's assume one based indexing, meaning the array's index has element n indexed from 1 to n. Now, similar to a segment tree, we will want to create another tree or another array which will sort of represent the different segments or the result of different segments of the original array. But the way we segment in the binary index tree is much different than how we do in segment tree. In segment tree, it's just half, 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 half. Uh, in binary index tree, it's sort of similar, but we do the indexing based on some bits, some bit magic. Now, let's look at that. So let's say n equals to 16. So now let's build these different 16 indexes in the binary index tree. So and let's write for each index, let's write their binary representation. All right. So I'm gonna build from 16. So I'm gonna do 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros and then 8 ones. 1, 2, 3, 4, 5, 6, 7, 8, and I'm gonna get rid of this stuff so that I can build it up now. So 8 zeros, 8 ones. I'm basically writing this binary representation of from 0 to 16. So 0, 0, 0, 0, 1, 1, 1, 1, and now 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and finally 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And we're going to write 1 to 16. So this is from 0 to 15. Let's also add 16, which will be 1, 0, 0, 0, 0. Right? So let me just quickly write these actual numbers. So this is 0, which you don't really care about, and because an indexing is actually from 1, so we go 1, 2, 3, 4, 5, 6. Now, so like we said, now each index in the binary tree has to represent a segment from the original tree. And how that comes is basically half of the nodes in the binary index tree would represent an individual element. Which half? So, and all of this depends upon the last one that you have in the binary representation. So for all the guys which have a last one on the first position itself on the right, all of them will represent single elements, right? So what I mean by that is this will represent a single element. So when say single element, that means itself only. So this will represent 1 to 1. This will represent 3 to 3 in the original array. This will represent 5. This will represent 6 in the original array. This will, not 6, a mistake. After 5, there is, so basically all the odd ones, they will just represent a single element. So just 7, this will represent just 9. This will represent just 11. This will represent just 13, and this will represent just 15, right? And so that's the first way. And then for so half of the elements just represent a single node, right? After that, we divide further. So out of 16, 8 elements represented just a single node. And then divide 8 by 2 further, which is 4. So roughly 4 elements will actually be responsible for 2 elements. So all of these nodes will just responsible for single nodes. Now we'll look at 4 nodes which will be responsible for two nodes. And how is that happening? It all depends upon which is your first one, what is your first set bit from the right side. So all of these, the first set bit was 1, so they are all responsible for 1 elements. Now, which for some of the guys, the first set bit is the second bit. So if you look at it, this 0, 1, note this guy, and then this is 0, 1, and then this is 0, 1, and then this is 0, 1. So for all of them, they will be responsible for not one but two elements. So itself and the one above it, right? That's how to always yourself and above. So these guys will be responsible for two elements. So what that means is now this guy is responsible for two elements. So this is 14, and it will be responsible for two elements. So everything lesser than, right? So you want to go, this will be responsible for 13 and 14, right? And then this guy, so this guy again for two, so this will be responsible for 9 to 10 itself and one more before it, right? And then this guy will be responsible for 5 as well as 6. This guy will be responsible for 1 and 2. And similarly, now if we go further down, so let's maybe use a different color. Okay, let's use this purple color. And now we go further down. So 0, 1, now let's see where is 0, 0, 1. So this is 0, 0, 1. Is there any other 0, 0? This is also 0, 0, 1. So both of these guys will be responsible for four elements. All right, four elements. So this 12 is responsible till 12, but four before it. So 12, 11, 9, and all these four, right? So 12, 11, 9, and 12, 11, 10, and 9. So this is responsible for 9 to 12. Similarly, where is 0, 0, 1? This guy. So this guy is responsible for this guy. Total four elements. So from 1 to 4. All right. Now what else? Now let's find 0, 0, 0, 1. Okay. Let's use another different color. Maybe this orange. And 0, 0, 0, 1. Is there a 0, 0, 0, 1? Well, there is this 0, 0, 0, 1, and that's the only 0, 0, 0, 1. So this guy will be responsible for eight elements, right? So from 1 to 8. And I think we have covered everything except the last one, and this is 16, which is 0, 0, 0, 1. 0, 0, 0, 0, 1. This guy is responsible for how many elements? This guy is responsible for 16 elements. So this is responsible for all elements from 1 to 16. So this is the understanding or the complicated way of segmenting the tree, but this is how we have to build the tree first. So we know each tree in the each index in the binary index tree array, what all elements does it represent in the from the original array. Now let's take the example of sum, right? So what all of this would mean is the value at index 1 would be just the first node, the value at index 2 would be the sum of element 1 and element 2, value at index 3 will be just 3, value at index 4 will be the sum from 1 to 3 to 3 to 4. Now what are the two typical queries, right? One is range sum, right? So and here we'll handle prefix sum. So now let's say the question is this: tell me the prefix sum for 13. So what that means is tell me the sum from 1 to 13 in the original array, right? How do you do that now? Using this binary tree. Well, so what is a binary representation of 13? 13 is 1, 1, 0, 1, 1, 1, 0, 1. So the way to do that would be, so if you want to get the prefix sum for 1 to 13, well, you first get the value from this node, 1101 itself in the binary tree, which represents what? So if you look at 13, 13 just represents itself. So you will get just 13 here. Plus you remove the last one from this. Remove this one from this. So you go 1100. What does this guy this which is what is 1100? 1100 is 12. What are all the values in the original array is 12 capable or is 12 responsible for? It is 9 to 12. So from this you get 9 to 12 and keep doing that. Now you remove this one further, you remove this one, you go 1000. What is this guy responsible for? 1000 is 8. It is responsible for everything from 1 to 8, right? And if you remove further, it becomes 0. 0 is not responsible for anything. We don't care about 0. So this is where we stop. And so you go from 1 to 8 and then 9 to 12 and then 13. So you actually get the sum for all, right? So if you wanted to get the sum from 1 to 13, you just have to look at these three elements. And you can always imagine the number of such elements you would need is only depend the one number of bits, which will really depend upon the total number of nodes in the array, right? or a log of n, right? So number of bits will be log of n, right? So so essentially how many times you'll call this? Maximum will be log n, right? So that's why a prefix sum operation can be done in log n time. So this was how you would do a prefix sum. Now let's talk about how you would do update, right? So now I want to do update, and let's say same element at 13. I want to change its value to some other v. You can also look at this as I want to add some diff to the index 13, right? So this is index, right? So at index 13, I want to add some diff, right? So what that would mean is all the nodes which are responsible for 13 have to be updated, right? Not just the individual element 13, but each and every node that is responsible for 13. And what are all those nodes? This itself, this one as well, and this one as well. These three nodes are responsible for 13. How do you find those nodes now? Now, what is there a simple logic? Like for prefix sum, it was quite basic, right? We could just keep removing one from the end, and that would just give us the next node. Well, you can do the same thing for update as well. So 13 is what? Again, so 13 is 1101. So what are all the nodes that have to be updated? Well, first, obviously just yourself, and then whichever is your last one, add a one there. So what I mean by that, so 1101. Earlier we were removing the last one. Now we add a one at the last one position. So we add a one here. Whatever you get 1110. So you have to update this guy. You have to update 1110, and then keep doing it till the largest value possible. So 1110. You add a one at the last one. So this is the last one. You add a one here. So you go 0, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, which comes here, which is 16. So 1, 0, 0, 0, 0. You know, 16 is the largest that we support. After we don't have an index outside of that. So these are the three guys that have to be updated. This is 13. This is 8 plus 4, 12 plus 2. This is 14. And this is 16. 13, 14, and 16 needs to be updated if you're updating the element 13 in the original array, which is what we just saw here, right? So 13 was 13, 14, and 16 needs to be updated. So that is the typical or the primary way the binary indexed tree works. That both the prefix sum and updates will depend upon the number of bits. The number of bits is log of n, right? And this interesting way of representing the or segmenting your tree in this sort of power of two fashion gives you this capability to do the prefix sums and update in a sort of a the logarithmic time. Now, if we have to come to code about it, right? So let's talk about the code bit a little bit. So prefix sum. So in the prefix sum, what we're doing is we're saying I want to get prefix sum of index. So what we're really doing is that we're doing sum plus equals to. So we go initially we go create index, and then we come to a different index. Now how do we get to a different how do we get to that different index? So essentially what we are really doing in both when we're adding the last sum or we're removing the last sum, we're getting a specific bit mask, which is whichever is the last one. So for example, for 1100 what we're really trying to get is this value 100, right? And then we are subtracting these two. So this becomes 1000. Similarly, if let's say you have 1100 and you're doing the update thing, then you would want to add 1000 to it. So there we're subtracting, and then here you were adding. And you would go 00, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, and you'll get to this. So, okay, so that is clear that you're going to do here index minus equals to, so you're subtracting this index with something. Now the question is, how do you get this guy? And I would recommend you to go through some literature on this, but essentially you have to do index and minus index to be able to replace to be able to get to this 1000. Now I can try and explain it a little bit. So let's say your index, right? So essentially you're saying it's I want to find the first one, right? So this is ones, all ones, or rather anything, right? So you have a x, sum, and then this is your first one, and then before this first one, all you had were zeros, right? So this is your index, right? Now, what is minus index? Well, minus index is essentially 2's complement, right? So 2's complement is first you flip all the bits. So when you flip all the bits, x will become x complement, 1 will become 0, and z will become all ones, right? Z will become all ones. So we can do it z complement. And two, so this is 1's complement. And then 2's complement would be you have to add a 1 here, right? So 2's complement, you have to add a 1 here. So if you remember what zero complement is, zero complement will be all ones. So when if you do all ones and you do add 1 to it, what actually will happen? So what actually will happen is what this is z is all z complement is all ones, so all ones like this. And if you add a 1 to it, well, you will get a 1 0 and everything else will become 0, right? So all this z complement will again become z, and this 1 will come here, this will become 1, and this x complement will remain x complement, right? Now if I do index and minus index, right? So index is x, oops, so index is x1z and minus index is x complement 1z. And if you add all of them, what will you get? Well, x and x complement would be 0, so all zeros. So we can just say z, and then you'll get a 1, 1 and 1, and 0 and 0 would be 0, right? This is exactly what we wanted, right? This is the mask that you wanted. All zeros, just a single bit set, and then all zeros. So if you want to get this bit map with just a last set bit actually set, you just do index and minus index. So that's the bit, which is why we do this. So we wanted to subtract this mask you get by index and minus index, and you subtract it from this, and you do this till index is greater than 0, right? And that's it. This is how you do prefix sums. And now what about updates? Well, updates is again similar. So for update, we are doing add. So let's say we do add. We wanted to add to this index this value v, right? So what this would do is okay, so your tree, so you go tree of this index. In this, you will add this v, but not just this index. You want to keep it adding it for to all the nodes which are responsible to this guy, right? So that would mean now you would want to do index, and the way to reach there we say is that if you are 1100, the next guy who is responsible for you for that, you have to just add a 1 here, essentially, which is add this 100, right? Which essentially is, so you are adding this mask, which is index and minus index, and you keep doing this till when? You keep doing this till index is less than the largest index, which you can say just n, right? Less than equals to n, right? Till index is less than or equal to n, you keep doing this. So that's the basic idea for Fenwick tree or a binary index tree and doing the prefix sums. And obviously, if you want to range sum, you can do prefix sum minus prefix sum, right? So range from I1 to I2 would be okay. Prefix sum I2 minus prefix sums I1 minus 1, right? That's the basic idea. So range sum is also easy to find.